Good morning. Here we are once again at the physics video lecture. Physics 105A video lecture 17. We're talking about oscillations, and we're going to move on to what are called driven oscillations. So let's set that up. Driven oscillations still one-dimensional mechanics, so if we write down our Newton's law and then start to fill in what we've been working on, of course we have first our linear restoring force, Hooke's law restoring force, but now we've added and that one gets a minus sign because it opposes the direction of motion. We've added that frictional force and we've worked with that. Now we're going to add a driving force that is explicitly, I'll just put a subscript, driving force, that is explicitly a function of time. Good. So this is called the damped driven oscillation because it has a damping term right there. There's the driving force. Now before I move on, I'm going to bring a demonstration into play. And let's see here. Tip the camera down a bit. There we go. This is the all-time driven oscillation demonstration, okay? So we have oscillating systems, and we happen to have three of them here, kind of an inverted pendulum on a spoke, and you can count out the period or the frequency pretty easily. This one's a little faster, okay? And finally, this one here, a lot faster. So those are oscillators, and in fact, those would be this differential equation without the driving force. Okay. So without the driving force, we have a damped oscillation, and we'll do the middle one here. And if you wait a little while, you can even see the amplitude is decreasing. And if you wait long enough, it will decrease to zero. That's good enough, right? This one here, we would have to wait a lot longer. But it too would be a damped oscillation. So what about the driven? The driving force is anybody who's acting on this handle right here, and you just drive this system back and forth. But there's an interesting property that we're going to investigate in detail, and that is that if I drive it with a particular frequency, one of the oscillators responded. This one right here, the other two were essentially unaffected by it. So once again, if you count out the frequency here, okay, count out how fast that goes, and then compare to the driving frequency with my hand, okay, you'll see they're essentially the same, and we're getting what's called resonance because those oscillations keep growing, even though I'm not really doing much. I can do the same thing for the middle oscillator here, and again, just count out its oscillation frequency. We get a feel for what the period is there. And then if I drive it with that same frequency, I can get the middle one to respond, the other two not, okay? So you can see driven oscillations have some interesting properties here. And that'll be this differential equation. The driving force was me, and the damping and the linear response to it and the mass are all pretty clear as well. Good. So I'm going to remove that. go back to the full board. There we go. So let's continue to work on these things right here. This, when we go ahead to solve it, we will bring these two to the left side, and I'll do it, and divide by the mass the way we did before. So now our differential equation is 2 time derivatives plus the 2 gamma 1 time derivative omega naught squared x, and what's left on the right side is f of t over m. I'll ignore the subscript there. And of course what we've done is omega naught squared is k over m, and 2 gamma is b over m, just as before. So let's focus on this thing right here. So this is what's called an inhomogeneous linear differential equation, because instead of a 0 on the right side, it has something. Okay. So this is the inhomogeneous equation. And if we're talking about this equation star, we can also talk about it, the homogeneous equation, which would just be the left side being equal to 0. So there's some terminology here. Inhomogeneous linear differential equation. Got ahead of myself there. Linear differential equation, and that's because it has that on the right side. So we're going to study a couple versions of this equation. There's a real rich phenomenology that I started to show you there, and it's an important case. What we're going to start with is the undamped version of this, where we have an interesting specialized technique. Okay, so driven oscillations, these are actually damped driven oscillations because of that right there. So let's make sure we have that down as well. Damped driven oscillations. Driven just refers to net force. Okay, so we can put, we'll also write homogeneous when it equals 0. Okay, inhomogeneous when it has this part right there. Good, so let's get started with the undamped driven oscillation. So first case, we're looking at B is equal to 0, no damping, and then what's our differential equation? Plus omega naught squared x is equal to f of t divided by m. Okay. So now I'm going to introduce a technique of solution of this. Very general, takes us right back into our complex numbers. So what we do is, I'll write here solution using complex numbers, just to warn you. what we're going to do is let this letter C be x dot plus I omega naught times x. And what we're saying is x is actually what we're looking for, right? X of t. So x is a real number, x dot is a real number as well. So x is the solution, the position with respect to time, x dot is the velocity, and what we've done is we've combined the two by adding x dot plus I omega naught x. We've combined them into a complex number. Now why would we do that? Let's take a derivative and we get second derivative here plus I omega naught first derivative x dot. And now what we can do is the following: C dot minus I omega naught times this C is going to be x second derivative plus I omega naught x dot. And I'm going to subtract I omega naught times what I have here already, x dot plus I omega naught x. So we get a cancellation. I omega naught x dot minus I omega naught x dot. So that leaves us with x double dot. Those go away. Minus I times plus I is plus, okay. Minus I times I is positive 1 omega naught squared. So that's interesting because this is our differential equation, or this is the left side of our differential equation. So now we can actually say the following. We have C dot minus I omega naught C is equal to, right, the right side of our differential equation, which is f of t over m. So what has this trick done here? We've gone into the complex numbers and we've reduced the order of the differential equation from a second order equation to a first order equation. Okay. So let's even write that down as a note. Reduction to, or reduction from second to first order. Second to first order. Right. It's like we're halfway there. Now, just as with our original equation, it's inhomogeneous, and the homogeneous solution would be very easy to find. So that's what we're going to do next. So we're trying to solve the equation in the black box. The homogeneous equation would be C dot minus I omega naught C is equal to 0. Well, what's the solution to that? For C dt is equal to I omega naught times C, you recognize what we've just been talking about. Linear differential equation with constant coefficients. The general solution is a complex exponential with C of t is equal to a e to the I omega naught t. Okay, that makes sense? If I take the derivative here, bring down I omega naught. and then I omega naught times the original. So we immediately know that for the homogeneous equation, we would be done. Of course, that's not what we're actually here for. We have to do the inhomogeneous equation. So the technique to solve the inhomogeneous equation is to turn this amplitude into a function of time. So that's going to be our trial solution. So the inhomogeneous equation which is this right here, is going to be solved by a technique called variation of constants, of which I recall there being a couple techniques named that. So solved by, I'll just put this in quotes here, variation of constants. In this case, we're going to take this as a function of time. So let our trial solution be equal to a of t e to the I omega naught t. And of course, what's going to happen in the solution that we end up with is if f of t vanishes. Okay, so if f of t if you plug in f of t equals 0, this general solution is going to have a of t as a constant. Okay, so that's our trial solution, as we call it. Be the trial solution. Now we'll just go in there into this differential equation. So we take a derivative minus I omega naught times the function itself equals f of t over m. So here we go. C dot minus I omega naught c. So what is that equal to? It's equal to dA dt e to the I omega naught t plus a of t I omega naught e to the I omega naught t. And that is supposed to be equal to f of t over m. Oh, not so fast. So that was just the first term here. So now I have to subtract off minus I omega naught c. Minus I omega naught c is equal to f of t over m. But what you'll notice is that this is I omega naught times c. Okay, I omega naught parentheses times a e to the I omega naught t. So these two are equal to 0, and I'm now left with, I'll work right here, I'm now left with dA dt e to the I omega naught t is equal to f of t divided by m. And we're almost there. So we'll have to return to this. So not only is this first order, but in fact we can just solve it by direct integration. We'll do one more step. Let's multiply both sides e to the minus I omega naught t. So continuing here, dA dt equal to f of t over m e to the minus I omega naught t. and then we'll integrate and find a. And a of t is going to be equal to integral f of t, got to put a prime there, e to the minus I omega naught t prime dt prime from 0 to t. And because when t equals 0, this whole integral is equal to 0, we will write plus c sub 0. Okay, that's a constant. And let's see, let's go ahead and write down the whole thing now. Finally, we have this, of course, is what we're looking for. And we have found this a of t. We'll go ahead and multiply this on the left side. So e to the I omega naught t, and then I'll put this in parentheses. 0 to t, f of t over m t prime, e to the minus I omega naught t prime, plus this initial condition. This clearly becomes the initial condition. Okay, when t is equal to 0, this entire integral is 0. This is 1, right? E to the 0 is 1, and we have c of t equals its initial condition. So I'll just write here as a note, c sub 0 is equal to x dot sub 0 plus I omega naught x sub 0, right? Initial conditions. Initial conditions. Okay, so now we have to work with this very interesting recipe. You know, you might be wondering, well, where's x of t? We set out to find x of t, and now we have this complex number. So our solution, x of t, I'll write there, our solution x of t question mark. Well, x dot plus I omega naught x. So everything is real here. Well, what's real? X dot is real, x is real, omega naught is real. So this is a complex number. This here, in parentheses, is the imaginary part of that complex number, and x is the imaginary part of the complex number divided by omega naught. So x is equal to the imaginary part of our solution, c, divided by omega naught. Perfect little trek through some complex analysis here, right? So there we have an actual method. This is how to do the thing. Of course, I don't have the original differential equation up here, but you had your original undamped differential equation with the driving force, and you just construct this solution. Now you do this integral, worry about the initial condition, and then take the imaginary part when you finally get it and divide by omega naught. Okay, so we're going to do an example of this. You consult the clock. Yeah, I'll do an example and I'll give one for you guys to do on homework. And here's what I'll do. I'll leave that recipe up there. I'll even remind us of what our differential equation was. is what we started with. And up on the next board, we'll do the simplest case, which is instructive, namely the constant force. Let me make some room here, and that should just fit on one board. Okay, let's write down our example. F of t is simply equal to a constant. We'll just call it F naught. Okay? So we've got a constant there. Everything that we have to do is up here, so we're going to go straight to this integration here. So now what do we have? We want to construct our integral 0 to t F naught divided by m e to the minus I omega naught t prime dt prime. So that's the first thing. We'll go ahead and get that equals F naught over m. So what about this integral of the exponential? Well, we just treat it the way we treat any function. And so we would integrate with 1 over negative I omega naught e to the negative I omega naught t prime from 0 to t. So we've got F naught over m, 1 over negative I omega naught e to the minus I omega naught t minus 1. And we'll just leave that. And now we're going to multiply e to the I omega naught t to that right there. You notice this will multiply both objects in our parentheses. I haven't written down c sub 0 yet. And c of t is equal to F naught over m, 1 over minus I omega naught. And then you'll notice e to the I, e to the minus I omega naught t, that gives us a 1 minus e to the I omega naught t. Now I still have that unspecified initial condition plus, so c sub 0 e to the I omega naught t as well. So now we're done, except we have to pull out the imaginary part and divide by omega naught. What I'm going to do is let c sub 0 equal 0. Remember, that's just an initial condition. That means my system's going to be at rest with no initial velocity. So x, got enough room here? Sure. X of t is equal to the imaginary part of c over omega naught. Well, I'm going to free up a little room. I can use this side of the board. So what do we have here? Here we are. Okay, so imaginary part part over omega naught. I'm gonna have to write out the entire thing because we don't quite see it yet. So we have F naught over M. We have 1 over negative I omega naught. I can multiply both of those by I, so I would have I over omega naught. Okay, that's an important trick. Multiply top and bottom by I have I times negative I is 1. Okay, so I over omega naught. 1 minus, I'm going to write just a little small, e to the I omega naught t is cos omega naught t plus I sine omega naught t by Euler's formula. And the imaginary part is going to be the one that multiplies real part there. So let's give us a little more room. Imaginary part over omega F naught over M I over omega naught 1 minus cosine omega naught t minus I sine omega naught t. Okay. So I just make the point. I times I is going to be real, and therefore what we're looking at for our imaginary part by omega naught is just everything except for that. So what do we end up with? We get F naught over M omega naught squared times 1 minus cosine omega naught t. So that's our solution. Where have we seen that before? It's really just a harmonic oscillation that's been shifted. So a constant force just shifts the origin for harmonic oscillation. Yeah, right under here, let me give an example. Example. Suppose we have a mass hanging on a spring, and I'll make the positive direction in the down direction. Okay. So the constant force for a mass on a spring, here the constant force is F naught equals mg, right? So we would have x of t would be equal to mg over m omega naught squared times 1 minus cos omega naught t. And not only that, it might be better to do this. We've got the mg. Fine. What about the m omega naught squared? Remember that omega naught squared is equal to k over m. So this m omega naught squared is just k. mg over k. And of course the mg over kx is the new, gives us the new equilibrium position. So if you had your mg pointing down and your k, x 0 pointing up, that would be your, or k delta x if you wanted to, that would be your new that would be the free body diagram that gives you your new equilibrium position. Okay, so this thing is completely understood at that point. In fact, one more thing. If you release this thing from rest when the spring is completely relaxed, then that's your origin. So if you release it from rest from your origin, you've got a zero everywhere. And then at half a period, you're going to have 1 minus negative 1. You're going to have 2 times the full amplitude. Okay. Good. So yeah, this is worth the analysis. It really shows everything. Okay, I'm going to consult the clock again. I want to give you guys a problem to do. Yeah, perfect time. So for your homework, let's see. This board actually has everything up on it still, doesn't it? Yes, it does. So let me go ahead and erase all of this. So I calculated this example. For your homework, we're going to just go up one little notch and do a linear force. So homework problem. C of t and x equals imaginary part of c over omega naught, right? This is what we really want for f of t is just some constant times t. Okay, so this is a force that grows linearly in time. And what you're going to find is let's go ahead and make let c sub 0 equals 0. So just letting the initial condition be 0 is no big deal. Simplifies things. It means that our particle is at rest when we initially start. You see, it's a driven oscillation, so it's going to get going one way or the other. Okay. So we'll let this be at rest. And here's what you have to do. You go in and when you calculate this integral, instead of a constant, now you have a t, b times t. So you're going to, right, so f is b times t. What you're going to have to do is one integration by parts, okay? But otherwise you treat these things carefully the same way we did. So I'll just put here a little note. You're going to have to do integration by parts. And then you have to carefully divide out the real and imaginary parts of your final result here. And then it's the imaginary part, so the part that's multiplied by I, that you isolate and divide by omega 0, and that gives you your result. So calculate this. Here, I'll make this a two-parter. To sketch the graph of your solution. That's always good practice if you can do it. Sketch the graph of the solution. Good. So that's a nice problem. We're going to come back to this topic and try to work out the resonance catastrophe, the resonant phenomenon that I showed you with the all-time demonstration there. But we'll leave it at that and see you guys next time.